Tonight, tonight, tonight. Dude, there is so much lightning and thunder outside in this house. Watch this. When I open the window, there's gonna be a crazy lot of things happening here. Me hi, me hi, me hi, me hi. Bro. Guess who? It's me. Bro. Shut up, Grim. It's raining pretty hard. It sounds fun out there. Pretty cool, innit? G, -9. That would be 1. Enter. There we go. 2. So 2. That would be -5. Oh. That was a pretty light boom, wasn't it? That was pretty loud. Oh. Oh, wow, wow, wow. Oh. Bruh. Oh, it's getting harder out there. Isn't it? Why would that move that right around? Okay. Okay. -1 on. What? In the wild? What? -what? 7? Okay, good. G. 4. It smells like rain. Smells like rain.
We're asked to evaluate -2 times f of -6 plus g of 1. And they've defined, at least graphically, f of x and g of x here below. So let's see how we can evaluate this. Well, to do this, we first have to figure out what f of -6 is. So our input into our function is -6. So, and we'll assume that's along the horizontal axis. So our input is -6. And based on our function definition, f of -6 is 7. So this thing, let me write this down. F
6, 7.
of -6 is equal to 7. And what is g of 1?
6, 7.
G of 1, well, once again, here's our input axis. And then the function says that g of 1, which is right over there, is -5. G of 1 is equal to -5. So this statement simplifies to -2 times f of -6, which is 7. So times 7 plus g of 1, which is negative 5. So plus negative 5, which simplifies to, let's see, negative 2 times 7 is negative 14 plus negative 5, which is negative 19. And we are done.
It's raining mildly. What if I switch it to desktop? No. Hello. There we go. There we go. There we go. Oh, oh, oh. God, I hate Mondays. I don't like Mondays. Why does it sound so bad now? God,
Hello.
I hate Mondays. It's not going through the right microphone, is it? I don't like Mondays. Why does it sound so bad now? Oh, but don't. Yeah, you sniffing at the air there, you little dog. Little dog girl. Let's go. I don't know. I prefer reading things. F negative 9? Oh, F negative 9. Hmm. So that would be F negative, okay, negative 1. F9 times F, negative 1 times F plus 7 times G. I like a G6. Boom, 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 boom. G6. Okay, I see now. Take a photo of that, memorize it. Actually, I'm not memorizing it. Okay. So what I needed to do. Oh God, I forgot already. When do they gotta get picked up? When do they gotta get picked up? 3:10. Well, when you go pick them up, would you mind if I went with? Okay, good. Thank you. No, I want it open. Oh. I like the smell of the rain. Dum, 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 dum. Why do I have these lines? Probably from smiling. No, 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 no. Okay, whatever, I'm good. I don't remember what was done. Don't. Okay, F4, F negative. F negative 4 equals negative 3. Oh, okay, yeah. Okay, F negative 8. F negative 8 is negative 2. Negative 3 times 2. Wait, no. Yes, that would be negative 8. That's negative 2. And, I think a house or something caught on fire because, boom. Okay, G2. G2 is negative 4. Huh? Maybe. Or something got set on fire because I keep hearing. Because now I'm hearing like, woo. I hear woo woos. Yeah, I want to go with him. It's 7 times negative 4, negative 4. -4. -22. Let's see. I got it. I'm smart. I'm intelligent. Okay, F -8, 8, 8. -8 is -5. That's 5. Parentheses. -5 and parentheses. Because that's how the photo worked. That's how the photo worked. That's how the photo worked. Yeah, why is there so many like car noises? Like wee woo, wee woo, wee woo. There's so many wee woos. Minus 4 times G4. So G4 would be 3. It's -7. It's -7. Okay. So -2 times -6 is going to be a negative. -2. -2 times -2 minus, good, 7 times -7, which is -3. 3. 25. What? Did I do something wrong, Mr. F? Oh, I did. So it wasn't a -2. I was looking at the wrong thing. There would be a +5 times 5 minus 7 times -3. Try again. Now it's 11. Oh, I just have to answer this bonus question. Okay, clear. 5 times F1, which would be -5. 5 plus 5 times 9. That would be -6. -55. Let's hope that's right. Okay, bonus question. -8. -8 times F0 should be 1 times 1 plus 4 times -8. 6. -32. Move, bruh. Easy. peasy, lemon squeezy. I did that. I did lesson 4.
What I hope to do in this video is get
Let me
familiar
stop.
with the notion of an interval and also think about ways that we can show an interval or interval notation. So right over here, I have a number line. Now let's say I wanted to talk about the interval on the number line that goes from, let's say, from -3 to 2. So I care about this. Let me do this in a different color. Let's say I care about this interval right over here. So I care about all of the numbers from -3 to 2. So in order to be more precise, I have to be clear. Am I including -3 and 2, or am I not including -3 and 2? Or maybe I'm just including one of them. So if I'm including -3 and 2, then I would fill them in. So this right over here, I'm filling -3 and 2 in, which means that -3 and 2 are part of this interval. And when you include the endpoints, this is called a closed interval. Closed interval. Closed interval. And I just showed you how I can depict it on a number line by actually filling in the endpoints. And there's multiple ways to talk about this interval mathematically. I could say that this is all of the, let's say this number line is showing different values for x. I could say these are all of the x's that are between -3 and 2, and 2. And notice I have -3 is less than or equal to x. So that's telling us that x could be equal to -3. And then we have x is less than or equal to +2. So that means that x could be equal to +2. So it is a closed interval. Now another way that we could depict this closed interval is we could say, okay, we're talking about the interval between, and we could use brackets because it's a closed interval, -3 and 2. And once again, I'm using brackets here. These brackets tell us that we include, so this bracket on the left say that we include -3, and this bracket on the right says that we include +2 in our interval. Now sometimes you might see things written a little bit more mathy. You might see something like that, like x is a member of the real numbers such that. So, and I could put these curly brackets around like this. These curly brackets say that we're talking about a set of values, and we're saying the set of all x's that are a member of the real numbers. So this is just fancy math notation to say member of the real numbers. I'm using the Greek letter epsilon right over here to say member of the real numbers such that this vertical line here means such that -3 is less than x is less than, or -3 is less than or equal to x is less than or equal to 2. I could also write it this way. I could write x is a member of the real numbers such that x is a member of this closed set. I'm including the endpoints here. So these are all different ways of denoting or depicting the same interval. But let's do some more examples here. So let me draw a number line again. So number line. And now let me just do an open interval. An open interval just so that we clearly can see the difference. So let's say that I want to talk about the values between -1 and 4. Let me do this in a different color. So the values between -1 and 4, but I don't want to include -1 and 4. So this is going to be an open interval. So I'm not going to include 4, and I'm not going to include -1. Notice I have open circles here. Over here I had closed circles. The closed circles told me that I included -3 and 2. Now I have open circles here. So that says that I'm not. It's all the values in between -1 and 4. So -1 or -0.9999999 is going to be included, but -1 is not going to be included. And 3.9999999 is going to be included, but 4 is not going to be included. So how would what would be the notation for this? Well, here we could say x is going to be a member of the real numbers such that -1, I'm not going to say less than or equal to because x can't be equal to -1. So -1 is strictly less than x is strictly less than 4. Notice, not less than or equal because I can't be equal to 4. 4 is not included. So that's one way to say it. Or another way, I could write it like this. X is a member of the real numbers such that x is a member of, now the interval is from -1 to 4, but I'm not going to use these brackets. These brackets say, hey, let me include the endpoints, but I'm not going to include them. So I'm going to put the parentheses right over here. The parentheses. So this tells us that we're dealing with an open interval. So this right over here, let me make it clear. This is an open interval. Now you're probably wondering, okay, in this case, both endpoints were included. It's a closed interval. In this case, both endpoints were excluded. It's an open interval. Can you have things that have one endpoint included and one endpoint excluded? And the answer is absolutely. Let's see an example of that. So I'll get another number line here. Another number line. And let's say that we want to, and actually let me do it the other way around. Let me write it first, and then I'll graph it. So let's say we're thinking about all of the x's that are a member of the real numbers such that, let's say -4, let's say -4 is not included, is less than x, is less than or equal to -1. So now -1 is included. So we're not going to include -4. -4 is strictly less than, not less than or equal to. So x can't be equal to -4, so open circle there. But x could be equal to -1. It has to be less than or equal to -1. So it could be equal to -1, so I'm going to fill that in right over there. And then it's everything in between. If I want to write it with this notation, I could write x is a member of the real numbers such that x is a member of the interval. So it's going to go between -4 and -1. But we're not including -4. We have an open circle here, so I'm going to put a parentheses on that side. But we are including -1. We are including -1. So we put a bracket on that side. And so that right over there would be the notation. Now there's other things that you could do with interval notation. You could say, well, hey, everything except for some value. So let me give another example of, let's get another example here. Let's say that we want to talk about all the real numbers except for 1. So we want to include all of the real numbers, except for 1. Except for 1. So we're going to exclude 1 right over here, so open circle, but it can be any other real number. So how would we denote this? Well, we could write x is a member of the real numbers such that x does not equal 1. So here I'm saying, look, x can be a member of the real numbers, but x cannot be equal to 1. It can be anything else, but it cannot be equal to 1. And there's other ways of denoting this exact same interval. You could say x is a member of the real numbers such that x is less than 1 or x is greater than 1. So you could write it just like that. Or you could do something interesting. This is the one that I would use. This is the shortest, and it makes it very clear. You're saying, hey, everything except for 1. But you can even do something fancy, like you could say x is a member of the real numbers such that x is a member of the set going from -infinity to 1, not including 1, or x is a member of the set going from, or a member of the interval going from 1, not including 1, all the way to positive infinity. And when you're talking about negative infinity or positive infinity, you always put a parentheses. And the view there is you can never include everything all the way up to infinity. It needs to be at least open at that endpoint, because infinity just keeps going on and on. So you always want to put a parentheses if you're talking about infinity or negative infinity. It's not really an endpoint. It keeps going on and on forever. So you use the notation for open interval, at least at that end. And notice we're not including 1 either. So if x is a member of this interval or that interval, it essentially can be anything other than 1. but this would have been the simplest notation to describe that. Let's have a little bit of a review of what a function is before we talk about what it means, what the domain of a function means. So a function we can view as something, so I'll put a function in this box here, and it takes inputs, and for a given input, it's going to produce an output, which we call f of x. So for example, let's say that we have the function, f of x is equal to 2 over x. So in this case, let me see. So if that's my function f, if I were to input the number 3, well, f of 3 that we're going to output, we know how to figure that out. We've defined it right over here. It's going to be equal to 2 over 3. It's going to be equal to 2 over 3. So we were able to, for that input, we were able to find an output. If our input was pi, then we input into our function, and then f of pi, when x is pi, we're going to output f of pi, which is equal to 2 over pi. So we could write this as 2 over pi. So we were able to find the output pretty easily. But now let's do something interesting. Let's attempt to input 0 into the function. If we input 0, does the function tell us what we need to output? Does this definition tell us what we need to output? So if I attempt to put x equals 0, then this definition would say f of 0 would be 2 over 0, but 2 over 0 is undefined. Let me write this, 2 over 0. This is undefined. This function definition does not tell us what to actually do with 0. It gives us an undefined answer. So this function is not defined here. It gives a question mark. So this gets to the essence of what domain is. Domain is the set of all inputs over which the function is defined. So the domain of this function f would be all real numbers except for x equals 0. So let me write down these big ideas. This is, so domain. A domain of a function. Actually, let me write that down. Domain of a function. A domain of a function is the set of all inputs over which the function is defined. Over which the function is defined, or the function has defined outputs, over which the function has defined outputs. So the domain for this f in particular, so the domain for this one, if I wanted to say its domain, I could say, look, it's going to be the set, and this curly brackets, these are kind of typical mathy set notation. I can say, okay, it's going to be the set of, and I'm going to put curly brackets like that. Well, x can be a member, this little symbol means a member of the real numbers, but it can't just be any real number. It can be most of the real numbers, except it cannot be 0, because we don't know this definition. It's undefined when you put an input of 0. So x is a member of the real numbers, and when we write real numbers, we write it with this kind of double stroke right over here. That's the set of all real numbers, such that, but we have to put the exception. 0 is not x equals 0 is not a member of that domain, such that x does not equal 0. Now let's make this a little bit more concrete by doing some more examples. The more examples we do, hopefully the clearer this will become. So let's say we have another function. And just to be clear, we don't always have to use f's and x's. We could say, let's say we have g of y is equal to the square root of y minus 6. So what's the domain here? What is the set of all inputs over which this function g is defined? So here we are inputting a y into function g, and we're going to output g of y. Well, it's going to be defined as long as whatever we have under the radical right over here is non-negative. If this becomes negative, our traditional principal root operator here is not defined. We need something that, if this ended up being a negative number, hey, well, how do you take the principal root of a negative number? And we're just saying this is kind of the traditional principal root operator. So y minus 6 needs to be greater than or equal to 0 in order for g to be defined for that input y. Or you could say, add 6 to both sides, y needs to be greater than or equal to 6. Or you could say g is defined for any inputs y that are greater than or equal to 6. So we could say the domain here, is the set of all y's that are a member of the real numbers such that they're also greater than or equal to 6. So hopefully this is starting to make some sense. And we're always used to functions defined this way, but you could even see functions that are defined in fairly exotic ways. You could see a function, let me say h of x. H of x could be defined as, it literally could be defined as, well, h of x is going to be 1 if x is equal to pi, and it's equal to 0 if x is equal to 3. Now, what's the domain here? And I encourage you to pause the video and think about it. Well, this function is actually only defined for 2 inputs. We know h of pi. If you input pi into it, we know you're going to output 1. And we know that if you input 3 into it, h of 3, when x equals 3, you're going to put some commas here. You're going to get a 0. But if you input anything else, what's h of 4 going to be? Well, it hasn't defined it. It's undefined. What's h of -1 going to be? It hasn't defined it. So the domain here, the domain of h is literally, it's just literally going to be the 2 valid inputs that x can be are 3 and pi. 3 and pi. These are the only valid inputs. These are the only 2 numbers over which this function is actually defined. So this hopefully starts to give you a flavor of why we care about domains. Not all functions are defined over all real numbers. Some are defined for only a small subset of real numbers, or for some other thing, or only whole numbers, or natural numbers, or positive numbers, or negative numbers, or they have exceptions. So we'll see that as we do more and more examples.
You're not turning it in an hour. You can leave it overnight.
As a little bit of a review, we know that if we have some function, let's call it f. We don't have to call it f, but f is the letter most typically used for functions. That if I give it an input, a valid input, if I give it a valid input and I use the variable x for that valid input, it is going to map that to an output. It is going to map that or produce, given this x, it's going to produce an output that we would call f of x. And we've already talked a little bit about the notion of a domain. A domain is the set of all of the inputs over which the function is defined. So if this is the domain here, and I take a value here and I put that in for x, then the function is going to output an f of x. If I take something that's outside of the domain, let me do that in a different color. If I take something that is outside of the domain and try to input it into this function, the function will say, hey, wait, I'm not defined for that thing that's outside of the domain. Now, another interesting thing to think about, and that's actually what the focus of this video is. Okay, we know the set of all the valid inputs, that's called the domain. But what about the set of all of the outputs that the function could actually produce? And we have a name for that. That is called the range of the function. So the range, and the most typical, there's actually a couple of definitions for range, but the most typical definition for range is the set of all possible outputs. So you input something from the domain, it's going to output something, and by definition, because we've outputted it from this function, that thing is going to be in the range. And if we take the set of all of the things that the function could output, that is going to make up the range. So this right over here is the set of all possible outputs. All possible outputs. So let's make that a little bit more concrete with an example. So let's say that I have the function f of x defined as, so once again, I'm going to input x's, and I have my function f, and I'm going to output f of x. And let's say the function definition here, the thing that tries to figure out, okay, given an x, what f of x do I produce? The definition says f of x is going to be equal to whatever my input is squared. Well, just as a little bit of a review, we know what the domain here is going to be. The domain is the set of all valid inputs. So what are the valid inputs here? Well, I could take any real number and input into this, and I could take any real number and I can square it. There's nothing wrong with that. And so the domain is all real numbers. All real numbers. But what's the range? I'll do that in a different color just to highlight it. What is going to be the range here? What is the set of all possible outputs? Well, if you think about it, actually, to help us think about it, let me actually draw a graph here of what this looks like. So the graph of f of x is equal to x squared is going to look something like this. So it's going to look something like this. I'm obviously hand drawing it, so it's not perfect. It's going to be a parabola with a vertex right here at the origin. So this is the graph. This is the graph y is equal to f of x. This, of course, is the x-axis. This, of course, is the y-axis. So let's think about it. What is the set of all possible outputs? Well, in this case, the set of all possible outputs is the set of all possible y's here. Well, we see y can take on any non-negative value. Y could be 0, y could be 1, y could be pi, y could be e, but y cannot be negative. So the range here is, the range, we could say it a couple of ways. We could say f of x, let me write it this way. F of x is a member of the real numbers such that f of x is greater than or equal to 0. We could write it that way. If we wanted to write it in less mathy notation, we could say that f of x is going to be greater than or equal to 0. F of x is not going to be negative. So any non-negative number, the set of all non-negative numbers, that is our range. Let's do another example of this just to make it a little bit clearer. Let's say that I had g of x. Let's say I have g of x. I'll do this in white. Let's say it's equal to x squared over x. So we could try to simplify g of x a little bit. We could say, hey, look, if I have x squared and I divide it by x, that's the same thing as g of x being equal to x. X squared over x is x, but we have to be careful because right over here, we have to, in our domain, x cannot be equal to 0. If x is equal to 0, we get 0 over 0, we get indeterminate form. So in order for this function to be the exact same function, we have to put that, because it's not obvious now from the definition, we have to say x cannot be equal to 0. So g of x is equal to x for any x as long as x is not equal to 0. Now these two function definitions are equivalent. And we could even graph it. We could graph it. It's going to look, I'm going to do a quick and dirty version of this graph. But it's going to look something like this. It's going to have a slope of 1, but it's going to have a hole right at 0 because it's not defined at 0. So it's going to look like this. So the domain here, the domain of G is going to be x is a member of the real numbers such that x does not equal 0. And the range is actually going to be the same thing. The range here is going to be, we could say f of x is a member of the real numbers such that f of x does not equal 0. F of x does not equal 0. So the domain is all real numbers except for 0. The range is all real numbers except for 0. So the big takeaway here is the range is all the set of all possible outputs of your function. The domain is a set of all valid inputs into your function.
reorganize it. This one. What would that one be right now? But and also make sure to remember to add that way if it gets flipped around. That's how I use it. Is there any other rules for that? You should probably take it back. You can trim off the bottom part. Or rip it off or whatever. Just that little hanging bit. It's a little annoying.
The function f of x is graphed what is its domain? So the way it's graphed right over here, we could assume that this is the entire function definition for f of x. So for example, if we say, well, what does f of x equal when x is equal to -9? Well, we go up here, we don't see it's graphed here. It's not defined for x equals -9 or x equals -8.5 or x equals -8. It's not defined for any of these values. It only starts getting defined at x equals -6. At x equals -6, f of x is equal to 5. And then it keeps getting defined. F of x is defined for x all the way from x equals -6 all the way to x equals 7. When x equals 7, f of x is equal to 5. You can take any x value between -6, including -6, and +7, including +7, and you just have to move up above that number wherever you are to find out what the value of the function is at that point. So the domain of this function definition, well, f of x is defined for any x that is greater than or equal to -6, or we could say -6 is less than or equal to x, which is less than or equal to 7. If x satisfies this condition right over here, the function is defined. So that's its domain. So let's check our answer. Let's do a few more of these. The function f of x is graphed. What is its domain? Well, exact similar argument. This function is not defined for x's -9, -8, all the way down, or all the way up, I should say, to -1. At -1, it starts getting defined. F of -1 is -5. So it's defined for -1 is less than or equal to x, and it's defined all the way up to x equals 7, including x equals 7. So this right over here, -1 is less than or equal to x is less than or equal to 7. The function is defined for any x that satisfies this double inequality right over here. Let's do a few more. The function f of x is graphed. What is its range? So now we're not thinking about the x's for which this function is defined. We're thinking about the set of y values. Where do all of the y values fall into? Well, let's see. The lowest possible y value, or the lowest possible value of f of x that we get here, looks like it's 0. The function never goes below 0. So f of x, so 0 is less than or equal to f of x. It does equal 0 right over here. F of -4 is 0. And then the highest y value, or the highest value that f of x obtains in this function definition is 8. F of 7 is 8. It never gets above 8, but it does equal 8 right over here at when x is equal to 7. So 0 is less than f of x, which is less than or equal to 8. So that's its range. Let's do a few more. This is kind of fun. The function f of x is graphed. What is its domain? So once again, this function is defined for -2. -2 is less than or equal to x, which is less than or equal to 5. If you give me an x anywhere in between -2 and 5, I can look at this graph to see where the function is defined. F of -2 is -4. F of -1 is -3, so on and so forth. And I can even pick the values in between these integers. So -2 is less than or equal to x, which is less than or equal to 5.
is the domain of G. What? Domain of H. -5, 2. 6, 6 and 7. What? Domain ranges. Okay. 3, 7. Okay. Range. Is that 7, 7. Easy peasy lemon squeezy. -7, 4. Yes, father. What are you doing now? And it's still being delivered to Mino's house? Okay. That sounds fun. domain of F. Hmm. 6, 6, 6, 2, 4, 7. -8, -4. Huh? -6. What's the range? Is it -1, 5, range -4, 2. Domain. Ooh. Photograph these ones. What's the domain of H? Gotta check that one. Seems rather easy. Oh. Okay, so that one is going to be the same as the other one, just as long as it is 7. Or just the domain of X, G. Let's graph that. Yeah, Oreo.
Pooja had a beautiful plant. The plant began sprouting 2 days before Pooja bought it, and she had it for 98 days before it died. At its tallest, the plant was 30 centimeters tall. All right. Let h of t denote the height of Pooja's plant h measured in centimeters, t days from the time she bought it. Which number type is more appropriate for the domain of the function? And they tell us whether it's integers or real numbers. So we just have to remind ourselves, the domain of a function, that's the set of all of the inputs for which the function is defined. And the inputs here, these are t, and it represents days. And if I input t, the number of days, into the function h, it'll output the height of the plant. So let's think about it. At first you might say, think in terms of 0 days, 1 days, 2 days, and you might be tempted to say integers, but why not think about 1.5 days or 3.175 days? So I don't see any reason why t couldn't be a subset of real numbers. Why you can think about, the 97.99th day. So I would say real numbers. And then they say define the interval of the domain. So t, let's see, the t would be defined up to 2 days before she bought the plant. So I would say that's t is equal to -2 all the way to 98 days. And t could be equal to -2, that would be 2 days before she bought it, or as high as 98. So let's think about it. So the interval, I would include -2. I would include the low point. So that's why I'm using the brackets. If I wanted t to be greater than, not greater than or equal to, I would do the parentheses. But since t could be equal to -2, I'm going to use the brackets. And at the high end, it's 98. And we're going to include 98. So I'm going to put the brackets there as well. So t would be a member of real numbers such that it is a member of this interval right over here. So t could be -2, but I guess you say -2 is going to be less than or equal to t, which is going to be less than or equal to 98. Let's check our answer. We got it right. In this video, we're going to do a few examples finding domains of functions. So let's say that we have the function f of x is equal to x plus 5 over x minus 2. What is going to be the domain of this function? Pause this video and try to figure that out. All right, now let's do it together. Now, the domain is the set of all x values that if we input it into this function, we're going to get a legitimate output. We're going to get a legitimate f of x. And so what's a situation where we would not get a legitimate f of x? Well, if we input an x value that makes this denominator equal to 0, then we're going to divide by 0, and that's going to be undefined. And so we could say the domain here is all real values of x such that x minus 2 does not equal 0. Now, typically, people would not want to just see that such that x minus 2 does not equal 0. And so we can simplify this a little bit so that we just have an x on the left-hand side. So if we add 2 to both sides of this, we would get, actually, let me just do that. Let me add 2 to both sides. So x minus 2 not equaling 0 is the same thing as x not equaling 2. And you could have done that in your head as well. If you wanted to keep x minus 2 from being 0, x just can't be equal to 2. And so typically people would say that the domain here is all real values of x such that x does not equal 2. Let's do another example. Let's say that we're told that g of x is equal to the principal root of x minus 7. What's the domain in this situation? What's the domain of g of x? Pause the video and try to figure that out. Well, we could say that the domain is going to be all real values of x such that, are we going to have to put any constraints on this? Well, when does a principal root function break down? Well, if we tried to find the principal root, the square root of a negative number, well, that would then break down. And so x minus 7, whatever we have under the radical here, needs to be greater than or equal to 0. So such that x minus 7 needs to be greater than or equal to 0. Now, another way to say that is if we add 7 to both sides of that, that would be saying that x needs to be greater than or equal to 7. So let me just write it that way. So such that x is greater than or equal to 7. So all I did is I said, all right, where could this thing break down? Well, if I get x values where this thing is negative, we're in trouble. So x needs to be greater, x minus 7, whatever we have in this under the radical, needs to be greater than or equal to 0. And so if you say that x minus 7 needs to be greater than or equal to 0, you add 7 to both sides, you get x needs to be greater than or equal to positive 7. Let's do one last example. Let's say we're told that h of x is equal to x minus 5 squared. What's the domain here? So let me write this down. The domain is all real values of x. Now, are we going to have to constrain this a little bit? Well, is there anything that would cause this to not evaluate to a defined value? Well, we can square any value. You to give me any real number, and if I square it, I'm just going to get another real number. And so x minus 5 can be equal to anything, and so x can be equal to anything. So here, the domain is all real values of x. We didn't have to constrain it in any way like we did the other two. The other two, when you deal with something in a denominator that could be equal to 0, then you got to make sure that that doesn't happen because that would get you an undefined value. And similarly, for a radical, you can't take the square root of a negative. And so we would, once again, have to constrain on that. Figure that out. Well, I'll do that up here. F of 3 is going to be equal to what? And you might already see some warning signs as to what's going to happen here in the denominator. But I'll just evaluate the whole thing. In the numerator, we get 3 plus 5. In the denominator, we get 3 minus 3. So this is going to be equal to 8 over 0. Now, what is 8 divided by 0? Well, we don't know. This is one of those fascinating things in mathematics. We haven't defined what happens when something is divided by 0. So 3 is not in the domain. The function is not defined there, not in domain. Let's do another example. Determine for each x value whether it is in the domain of g or not. So pause this video and try to work through all three of these. All right, so first of all, when x equals negative 3, do we get a legitimate g of x? So let's see, g of negative 3, if we try to evaluate, that's going to be the square root of 3 times negative 3, which is equal to the square root of negative 9. Well, with just a principal square root like this, we don't know how to evaluate this. So this is not in the domain. What about when x equals 0? Well, g of 0 is going to be equal to the square root of 3 times 0, which is equal to the square root of 0, which is equal to 0. So that gave us a legitimate result. So that is in the domain. And what about g of 2, or x equals 2? What does that give us a legitimate g of 2? Well, g of 2 is going to be equal to the square root of 3 times 2, which is equal to the square root of 6, which is a legitimate output. So x equals 2 is in the domain. Let's do one last example. So we're told this is h of x right over here. And once again, we have to figure out whether these x values are in the domain or not. Pause this video and see if you can work through that. All right, well, let's just first think about h of -1. What's that going to be equal to? -1, every place we see an x, we're going to replace it with a -1, minus 5 squared. Well, this is going to be equal to -6 squared. -6 squared, which is equal to positive 36, which is a very legitimate output. And so this is definitely in the domain. What about 5? So h of 5 is going to be equal to 5 minus 5 squared. Now you might be getting worried because you're seeing a 0 here, but it's not like we're trying to divide by 0. We're just squaring 0, which is completely legitimate. So 0 squared is just a 0. And so h of 5 is very much defined. So this is in the domain. Now, what about h of 10? Well, h of 10 is going to be equal to 10 minus 5 squared, which is equal to 5 squared, which is equal to 25. Once again, it's a very legitimate output. So the function is definitely defined for x equals 10. And we're done. Thomas has 400 candy bars in his shop, and each costs 50 cents. Let P of B denote the price P measured in dollars of a purchase of B candy bars. All right, I input B, the number of candy bars I want to buy, and P of B will tell me, well, what's the purchase price? It's really just going to take the number of candy bars and multiply it by 50 cents, but we don't have to worry about that just yet. Which number type is more appropriate for the domain of the function? So let's just remind ourselves, what is a domain of a function? A domain is a set of all inputs over which the function is defined. So it's the set of all b's, it's the set of all inputs over which P of B will produce a defined response. So let's think about it. Is it integers or real numbers? So I could buy, B could be 0 candy bars, 1 candy bars, 2 candy bars, all the way up to 400 candy bars. Could I have a fractional, could B be 0.372 of a candy bar? Well, if this is a normal candy shop, each candy bar is going to be in its own packet. It's going to be in a discrete chunk. You're not going to be able to buy 0.372 of a candy bar. You're either going to buy one more or none more. So you're going to buy 0, 1, 2, 3, all the way up to 400. So I would say integers, that the domain of this function is going to be a subset of integers. You can't have all real number inputs. Integers are obviously a subset of real numbers, but you can't say, hey, I'm going to buy pi candy bars, or I'm going to buy the square root of 2 candy bars. You're going to buy integer number of candy bars. Now they say define the interval of the domain. So the fewest candy bars I could buy are 0 candy bars. And I have to decide, do I put a bracket or do I put a parentheses? So I could actually buy 0 candy bars, so I'm going to put a bracket. If I put a parentheses, that means I could have values above 0, but not including 0. But I want to include 0, so I'm going to put the bracket there. So the least I could buy is 0, and then the most I could buy, the store has 400 candy bars, so that's the most I can buy. The most I could buy are 400 candy bars, and I can buy 400. So I would put brackets there as well. So the interval of the domain, I would want to select integers. So B is a member of integers such that B is also a member of this interval. It can be as low as 0, including 0, and as high as 400, including 400. Got it right.
Dad, can you get me like a card slide over there?
This right over here is a screenshot from a Khan Academy exercise, and it says Mason stands on the 5th step of a vertical ladder. The ladder has 15 steps, and the height difference between consecutive steps is 0.5 meters. He is thinking about moving up, down, or staying put. So let me draw this ladder that Mason is on. So it's a vertical ladder. So that's one side of the ladder. This is the other side of the ladder. And it has 15 steps. Let me see if I can draw that. So this is the first 1, 2, 3, 4. Actually, I'm going to run out of space. I need to make them closer together. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. 15 steps. Let me make sure it's even. So on the top and the bottom, and the difference, the distance between each of these, I guess you could say steps or the rungs of the ladder, are 0.5 meter. So this distance right over here is 0.5 meters. And it says that he's on the 5th step of this vertical ladder. So he's on the 5th step. So 1, 2, 3, 4, 5. So this is where he is right now. He's on this 5th step. And he's thinking about moving up or down or staying put. Let h of n denote the height above the ground, h of Mason's feet, measured in meters, after moving n steps. If Mason went down the ladder, n is negative. All right, h of n. So when he is denote the height above the ground after moving n steps. So let's just make sure we understand this. If I were to say h of 0, what is that going to be? Well, h of 0 means that he's moved 0 steps. If he's moved 0 steps, he's still going to be on this 5th step of the ladder. And so how high is he going to be? So if he's on the 5th step of a vertical ladder, so he is going to be, so I'm assuming that there's 0.5 from the ground. So this is the ground right over here. So he is 1, 2, 3, 4, 5 steps. Each of them is 0.5 meter. So 5 times 0.5 is going to give us 2.5 meters. So h of 0 is 2.5 meters. If I said h of 1, that means he goes up. H of 1 means he goes up 1 step. So here n would be equal to 1. So if he goes up 1 step, h of 1, he's going to be 0.5 meter higher. So is going to be equal to 3 meters. So we could keep doing that for a bunch of different inputs. So let me write that. That's going to be equal to 3 meters. But anyway, that's not what they're asking us about. They're saying which number type is more appropriate for the domain of the function. So the domain, just as a review, that's the set of numbers that we can input into the function and get a valid output. And it's clear here, so we have to pick between integers or real numbers. Well, n, which is our input, that's the number of steps he goes up or down. So it could be positive or negative, but we're not going to talk about half steps. Then he'll put his foot in the air right over here. He has to take integer valued steps up or down. Or I guess he's taking integer valued steps. If it's positive, it's up. If it's negative, it's down. If it's 0, that means he's staying put. If n is 0, that means he's staying put. It's not real numbers. He can't move pi steps from where he is. He can't move square root of 2 steps from he is. He can't even move 0.25 steps. Then he'd put his foot in the air. So this is definitely going to be about the integers, not the real numbers. This function right over here, the valid inputs, if I want to be able to input an integer. In fact, it's not even all integers because he can't go down an arbitrary amount. In fact, he can't go up an arbitrary amount either. But it's going to be, the domain is going to be a subset of integers. And then they say define the interval of the domain. And we have these little toggles here to think about, to define the interval of the domain. And let's see. The lowest value for n, he can go as far as 1, 2, 3, 4, 5 steps down. And in that case, n would be equal to -5. And then the highest value for n is if he takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps up. And so that would be n is equal to 10. So the interval of the domain, and actually I just copy and pasted this onto my scratch pad. N can be as low as -5 and as high as 10, and it can include them as well. So I'm going to use brackets. So my domain would include -5. If it didn't include -5, I'd put a parentheses, but I could put brackets here, and I could put brackets there as well. And I can actually, let me, just for fun, let me actually input it into the actual integers.
See my screen.
And I'm as low,
even with the sun on it.
5 steps, and I can go up 10 steps, and 10 is also included in my interval. And then I can check my answer, and I got it right.
How did I miss a spot? On my screen, I wiped my whole screen down. Oh my, I unplugged that. I already did this one. I already did this one. Oh. My little napkin that I use as my spacebar now. It flew away. I mean, as a delete backspace. I'm so glad that my computer's not hot at all.
Let's see if any of my assignments got graded yet. No.
No. Fine. Oh, that's new. That's cool. I like how Grim just stands around looking sad all the time. Poor Graham Cracker. Graham.